Oh, that's gross. Yeah, bottom row. All right. So you would use the GCD function in your calculator. So that's math. Go over to the NUM function. And then select GCD. All right, so we want GCD of 72 and 96. And it reports back to us that that's 24. And that's great because it just took a lot of the thinking out. All right. Now, if you were wondering how you might go about doing that by hand, that tree diagram that was on the handout, that's actually one of the ways to do it. So I'd look at 72, for example. I'd make a little tree diagram. And I would say, okay, two numbers. And you really can't go wrong. It's just your journey might be a little longer depending on what your initial factors are. But you just need to give me two numbers that you know multiply to 72. So what, just off the top of your head, what are two numbers that multiply to 72?
24 and 3.
24. Thank you. 24 and 3. All right. So then the other number, 96, we would create a tree diagram for that. Now, I didn't do a complete tree diagram for 72 because I want to see where things are going first. All right. So I would look for a breakdown of 96.
So 2 and 48. 2
and 48. All right. So then I would break down the appropriate tree diagram further. All right. So here I have a 48, which could be broken down further into what and what?
2 and 24.
2 and 24. The idea behind a GCF is to take the greatest factor that is in common between the two numbers. All right, so if I were to just list out these set of factors here, these sets of factors, I would get 3 times 24 and 2 times 2 times 24. So the largest factor that's in common between these two would be 24. All right. Now you may look at this and say, well, okay, well, that only worked out because you picked 24 and 3 to start. All right. Well, what if that didn't happen? So I take my 72. Well, 2 goes into 72, right? 2 goes into 36. 2 goes into 18. And then 9 could be broken up into a product of 3 and 3. All right. 96. 2 and 48, 2 and 24, 2 and 12, 2 and 6, 2 and 3. All right. So what you would do if you were to come up with these, this is the prime factorization tree. So if you were to break down your numbers, and this is where it gets really tedious because you're like, well, I got to do that in every single case. Well, no, you don't have to do it in every single case because I showed you on the calculator what you would do if you just want to get the right answer, but this is for understanding. What we would do is we would collect all the unique factors. So I have a 2 here, I have a 2 here, 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 that are in common. All right. So I'm at a 2's here, so I'm not going to continue collecting 2's. All right. I have a 3 here, I have a 3 here. I can't collect this 3 because I don't have a corresponding 3 over here. All right. So you're only going to collect factors that correspond from one set to the other. So I have a 2 that corresponds. And it happens 3 times, so 2 to the 3rd. And then I have a 3. 2 to the 3rd is what? Don't say 6. 8 times 3 is 24. So from the prime factorization trees, you can get it, but obviously it's a lot. That's a lot to write. If you had even a 10 question quiz or test, and you had to do this every time, you're going to spend most of the period just drawing the trees. Right? So that's definitely not the way to go. But it does help get a sense of how this thing works. You get to some less familiar numbers like 17 and 59. That's where you really want to stop thinking and let the calculator do the work for you. All right. What this is telling us is that the greatest common factor between these two numbers is 1, meaning that there is no meaningful common factor. There's no number that can divide, other than 1. 1 divides into anything. So there is no meaningful common factor between 17 and 59. But since they asked for the greatest common factor, we would state what it is. The GCF would be equal to 1. All right, and then we get to the variable cases. So the variable cases are interesting because the tree diagram approach, while it's cumbersome and boring and tedious for a number of situations, it's very useful when it comes to variable situations. All right, so I'm just going to take my x to the third, y to the fourth, at least thinking about it this way, and just list it off on the side. All right, I'd look at this and I'd say, well, an obvious breakdown would be to say, well, it's the product of x to the third and y to the fourth, right? So one branch would have x to the third. Another branch would have y to the fourth, which can be written as x times x times x, y, 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 y. Some of us are thinking that. Do the same thing with the x squared y. The natural split would be by variable, x squared and y. They each get their own branch. The y branch is complete. The x branch would go down to x times x. All right? So if I'm looking for my greatest common factor, what I'm going to do is collect unique corresponding factors. Right? So I usually start with the term that has less stuff going on with it. So I would say, okay, I got an x here, I got an x here. I have an x here, I have an x here. I have a y here, I have a y here. All right, I'm all out of terms, all out of factors for the x squared y term. So I can't collect more than what I have. So at this point, I'm done collecting terms. I have extra stuff here in the x cubed y to the fourth, but those terms, those factors are irrelevant. All right, so my GCF would be the set of factors that are in common to both. All right, so I have a pair of x's followed by a y, so x squared y. All right, so a shortcut. A visual shortcut more than anything else. You're going to look at each of the terms that make up the expression, and for each variable, you're just going to choose the term that has the highest power. The lowest power. That's the same common denominator. So going across the board here, I would say, okay, I have two terms. Each contains an x and a y. I want the x factor that has the lowest variable, the lowest power. That's that one. All right. I also want the y that has the lowest power. That would be that one. Sometimes it could be a mix and match between the two expressions. So I'll take this as typo bonus. An example 4 would be something like x to the third y squared z and x y to the third z to the second. All right. So I want to find the GCF between these two terms. I have three variables to work with. So GCF, I have an x, I have a y, I have a z. Find the x with the lowest power. Find the y with the lowest power. Find the z with the lowest power. Those are the powers that make up your GCF. X to the first, y to the second, and z to the first. Or you could just write it as x, y squared, z. All right. Though that is the term that would divide evenly into each of these factors. All right. And when I say divide evenly, it means that the result will not be a fraction. Right? If you end up with a fraction, if you were to test this out, if you want to check your work, if you were to test this out by dividing each of these terms by your greatest common factor, if you end up with a fraction, you did it wrong. Right? That's pretty much how it works. Okay, that's exactly how it works. So tiny now. All right, so factoring. We're going to be living in the world of factoring for the rest of high school. This is a concept, and it's all related to the GCF. This is a concept that never is ever going to go away, ever. So you might look at some of the topics that we've covered previously and say, well, you say that about everything. Inequalities, we haven't done anything with inequalities recently. What about properties? Things like that, those haven't come up. No, be patient, they will. They all come back at some point. The difference between this topic and those topics is that this is going to work its way into literally everything else that we do from here on out. So, today, in your senior year, you will use the concept of a GCF in your math class. All right. What I had on the board here, I erased it. It was literally this concept, which is related to the GCF. And I was doing that in AP Calculus. All right. So it never, ever, ever goes away. That's how important it is. All right. The earlier you get a good understanding of this, the better off you're going to be. This is the foundation of more advanced types of factoring. So again, solid understanding of this will pay off for you. All right. Factoring, reverse process of multiplication. Factor a polynomial by reversing the distribution process. All right. So undistributing, if you want. All right. We look for a GCF. So this is the first type of factoring. It's factoring by a GCF. All right. So we're undistributing, and we've touched on this already. We did this back in Unit 1, I think. All right. It's just we didn't formally have a unit on factoring, but now is the time for it. All right. So there's a solved example for you, but like a textbook, they have solved examples. Nobody ever reads them. You just go right to the problems, try them on your own. All right. What we want to do here is come up with a GCF. All right. First, that's our first goal. Come up with a GCF. We have two numerical components, the 20 and the 15. So the question that you might have is, all right, if, oh, this guy's aggravating me. I'm going to change his for you. So the numerical components you can put right in your calculator if you can't figure it out. If you can't think, because obviously if you can do it in your head, that's going to be better. But if you can't think to yourself, well, what is the largest number that could divide evenly into both 20 and 15? In this case, it's actually pretty easy. You could always do the GCD function in your calculator. Type in the 20, type in the 15. By the way, what is the answer going to be? 5. Calculator is going to tell us the same thing. All right, so numerically, we know that we're going to have a 5 in our GCF. Let me do that in blue. All right, now I have an x making up both parts of my expression. Each term has an x in it. So my GCF should have an x in it. I need the lowest power from any x that exists in my expression. So to the first power, because my lowest power is a 1. All right, you don't actually have to write 5x to the first. You can just write 5x. All right, but that's our GCF. That's the first step in the process. Next step is divide each term by 5x. So in the last unit, so it's our GCF again. In the last unit, when we were learning how to operate using monomials, multiplying, dividing, adding, subtracting, powers to powers, things like that, we were doing it to advance the cause here so that we would actually learn how to factor, right? It's just the underlying skills related to that. So I'm going to take the 20 x to the second and divide it by 5x. I'm actually going to show the steps here. 20x to the second divided by the 5x. And then I'm going to take my negative 15x and divide it by the 5x. So what do I get when I take 20x to the second and divide it by 5x? 4x. And what's 15x divided by 5x?
3x.
We got a 3 and we carry down the negative sign, so we get a negative 3. All right. So our job here is to represent this expression in factored form. What that means is that our new expression should have the same value as our original expression. Is 4x minus 3 the same thing as 20x squared minus 15x?
Yes. No.
No. All right. It would be if I multiplied it by what? 5x. All right. So what that's telling me is that the GCF is going to go out in front. All right. So we find the GCF. So if you like a process, here's your process. You find the GCF. Divide each term by the GCF. Put the GCF in front of your expression. All right. You can check it if you want. Check by distributing. 5x times 4x gives you 20x squared. 5x times negative 3 gives you negative 15x. All right. But that last expression there, 5x times 4x minus 3, that's your final answer. Because again, it's saying factor each polynomial. It's not saying divide each polynomial by the GCF. All right, so we're just using the division as a tool to help us come up with the factor form. But we still need the set of factors, one of which will be the GCF. All right, what would be the GCF in number 2?
11A.
11A. So then I'm going to take each term. We have a 44a squared. I'm going to divide that by 11a. I also have an 11a. I'm going to divide that by 11a. 44a squared divided by 11a is what?
4a.
4a. And 11a divided by 11a?
1.
1. So 4a plus 1. I'm going to pop that GCF right in front.
Simple.
If I distribute the 11a, will I get back where I started?
Yes.
Yes.
Yes. That's how you know you did it right.
Yes.
Now, the one thing you got to be careful about is sometimes you'll have pulled out a common factor, but it might not be the greatest common factor. So when you check by distributing, you may get back to where you started, but you may not have pulled out the correct GCF. So for example, if you thought the GCF was just an 11, so without the a, you would have come up with 11 times 4a squared plus a. That would still check out, but you wouldn't have pulled out the GCF, the greatest common factor, so you would have done something wrong there. All right. So they get a little bit more complicated, a little spicier. Sometimes we mix in multiple variables. Here I have a y and an x. So question, is there a common variable between the two terms?
No.
No. So the variables are irrelevant here. What would my GCF be?
12.
12. So 12 in the front. I don't have a variable here, so the thing that would make this complicated is not part of this problem. So if I divide each of these terms by 12, it should be pretty easy. What's 24y divided by 12?
2.
2y. And 36x divided by 12? 3x. All right. Looking at number 4, we have an s in the first term, we have a t in the second term, but I have no variable in the third term. So that's telling me that the variables aren't going to factor into the GCF. So my GCF is only going to be number-based, just like the last one. All right. So in this case, the possibilities are, well, you can reason it out. You can say, well, what's a number that can divide evenly into each of these?
4.
4. All right. You may want to do the GCD function on your calculator. If that's the case, the one drawback to this is that you can only work 2 terms at a time. So I'd pop in an 8 and a 20, get the GCD there, then do the same thing, but with the answer to the first round, so the 4, and then I pop in the 28. And we'll see that the GCF would still be a 4.
Wait, after you get to max, what do you hit?
What's that?
After you get to max, what do you put?
You keep going down.
Hit the down arrow. And yep,
okay.
there you go. All right, so my GCD is going to be 4. Now the question here, and it's a valuable question, do I want to take out a 4 as my GCF, or do I want to take out a negative 4?
No, 4.
4, regular 4.
Regular 4?
No, I'm
Yeah,
thinking
right?
negative 4 actually.
Negative 4?
Yes.
No, 4.
4.
Does it matter?
No.
Yes, because negative 4 doesn't go into 20.
That's,
Well, actually it does, but like...
that's incorrect.
If you do a negative 5.
Well, yeah.
You
So as it turns out, you can take out a 4 or a negative 4. It all depends, because a GCF, again, is the largest number that can divide evenly into whatever the expression is. But sometimes it's more beneficial to take out a negative, because it might change the look of a polynomial, and if it does, you might be able to do more with that expression. Just like when you distribute through with a negative number, you can undistribute a negative, right? So if you have a leading coefficient that's negative, maybe you need to undistribute a negative, right? So you could have 2 possibilities here. One possibility would be a 4 in the front. So negative 2s to the 4th plus 5t cubed minus 7. Or it might be a negative 4 in the front, in which case you have 2s to the 4th minus 5t cubed plus 7. All right, so how would you know to do a positive coefficient or a positive GCF versus a negative? In this case, you wouldn't know, but in other situations, you'll see. When we get to more advanced cases, it'll be more obvious when you want to take out a negative versus when you want to take out a positive. At this point, we're just learning that that's something that you can do. All right. Now, number 5. Let's take a look numerically first. I have a 6, an 18, and a 24. Largest number that divides evenly into all 3 of those? 6. And then for the variables, we have an n, and the highest power is a 1. All right. So then we're going to take each of those terms and divide by 6n. So what do I get when I divide 6n to the 6th by 6n? n to the 5th. Then 3n to the 3rd minus
4.
an even 4. All right. Let's see if I can clean that up a little bit. All right. What would be my GCF at number 6?
5. M.
5m squared.
No, so you say M. Yeah.
5m squared, or
minus
or as you said, negative 5m squared. All right, you got to be prepared to go both ways here. So possibilities: if it's a positive 5m squared, I'll put the 5m squared in front. What's going in the parentheses?
negative
Negative m squared.
Minus m 5m squared divided by 5m squared? 1. Anything divided by itself, right? So then other possibility would be to divide out a negative 5m squared. Now that we figured out what happens if you divide out a positive 5m squared, this should be very easy because it's made up of the same stuff, just the signs are reversed, right?
Yep.
So m squared plus m minus 1?
Yes.
Yep.
All right. Now, we haven't learned trinomial factoring yet, but here's a good example of why you might consider taking out a negative GCF as opposed to a positive one. When we learn trinomial factoring tomorrow, I think it's tomorrow, this is the form that we're going to want to have it in. This is not. All right. We want to have positive leading coefficients. If we have negative leading coefficients, it messes things up. Well, it's still doable. It's just not as efficient. 3H?
Yeah.
And how do we know there's no G in there, in the GCF?
Because 12H doesn't have a G.
Because 12H doesn't have a G. It only has, there's H's across the board, but we don't have G's across the board. All right, and the highest power of H is 1. And in terms of the numerical values, 3 is going to divide evenly into those. All right, so I pulled out a 3H. What am I going to have left inside the parentheses? G to the third minus
3G squared,
3G squared
plus 4.
plus 4.
Is it right there?
All right, number 8.
It would be 3. Yeah, it would be 3.
GCF, we're going to have a 3. We don't have X's across the board,
3y.
but we do have Y's, right? What's the highest power of, the lowest power of Y?
3.
3. So 3y cubed. Divided out of the first term. 2x to the second. Out of the second term.
Not 3xy.
3xy.
Not 3xy.
And then out of the last term.
And it would be 6y
6y
to the 4th.
6y to the
4th.
second.
Yeah, right. Oh, I see.
Where'd you get 4?
Because I didn't write the 3. It's like the 3 to the 4.
All right, and the last one, number 9. GCF.
Is 2HN
2H.
squared. No, not just regular N.
All right, so I pull out a 2HN. Divide the first term by 2HN. What do we get? 5H to the second n to the second. Yep. Minus second term.
N.
Just an n, right? Because the 2 is going to go away, the h is going to go away, n squared divided by n gives you an n. Plus a 7.
Nice.
Maybe a little too small. Just do it like that.